Hello, we are going to work through the Chapter 6 review for pre-calculus. So if you need a specific problem, feel free to just fast forward to the part that you need. We are going to do these in order, starting with number 1 here, which wants us to convert 280 degrees into radians. So if you recall, when you want to turn degrees into radians, you take the degrees and then you're going to multiply it by pi over 180 degrees. And then really your goal after that is just to reduce. So I'm going to reduce by first just dividing by 10. And then 28 over 18 can be further reduced down to, let's see, that would be 14 pi over 9. So that would be our answer there. All right, now if you're going to start with radians, in this case 11 pi over 12, to turn it into degrees, you multiply by 180 over pi. So here notice the pi's will cancel, and then if you just multiply straight across 11 times 180 and then divide by 12, you will get 165 degrees. All right. So in number 3, now we're going to use an arrow to draw the given angle in standard position, name the reference angle for the given angle, and find the exact value of the trig function. And then I also want you to make sure that you be sure to use rays to show the initial and terminal sides of the angles. So if we have 300 degrees, remember, all the way around the circle is 360, so we're going to be somewhere in the 4th quadrant here. So approximately here is where we would end up. And this is our theta. So theta is this very large angle here, is 300 degrees. So our reference angle, which we call theta bar, is going to be this degree measure here, which is 60 degrees. So remember the reference angle is always the shortest distance to the closest x-axis. So this would be our reference angle is 60 degrees. All right, so now to find the sine of 300 degrees, we need to determine what terminal point this is at. So if you recall from the unit circle, this would be the point 1/2 comma negative root 3 over 2. And when we're talking about sine, we are interested in the y value of that terminal point, which is negative root 3 over 2. Okay, so another problem similar to that. Oh, I did forget one thing here. It does say that it wants us to use rays to show the initial and terminal sides of the angle. So the initial side is always on this portion of the x-axis. So this would be the initial right here, and then this would be the terminal ray. Okay, so please make sure, I know it's a little redundant, but you do need a ray on the x-axis there. All right, so in this next problem, we have 585 degrees. So what I'm thinking is that first I'm going to have to go around 360, which is going to leave me with 225. And if you go 180 degrees, that gets you here, and then 45 more degrees would get you here into quadrant 3. And it turns out that this ray right here is going to be 45 degrees away from this x-axis. So our reference angle is going to be theta bar, and that is going to be 45 degrees. And that is coming from the fact that theta, the entire angle, was 565 degrees. All right, so that answers the first part of this question, that theta bar is 45 degrees. And then just like we did in the last problem, we have to figure out what terminal point that brings us to. Well, again, from your unit circle, this is negative root 2 over 2, comma, negative root 2 over 2, which Cosine, we care about the x coordinate, which is negative root 2 over 2. All right, and then number 4 is asking for the radian measure of angle theta. So here we're going to start to get into that formula for finding the length of an arc. So this 14 here is actually S, which is the arc length. Theta is just theta, and then the 4 here is the radius. So we are going to use the formula S equals R times theta and solve that for theta. All right, so the S we'll plug in is 14, R is 4, and then theta. And if we divide by 4, we'll get 14 over 4, which you could reduce down to 7 over 2 is theta. And I would recommend just leaving that as an improper fraction. If you want to turn it into a decimal, 3.5 is totally fine. Okay, now we're going to use some SOHCAHTOA here. So remember, sine is your opposite over your hypotenuse. And we're looking at this with respect to angle B. Opposite would be the 12 over here. And then the hypotenuse, of course, is 13. So that'd be 12/13. For tangent, remember that is your opposite over your adjacent. And we're looking with respect to angle A here. So opposite would be 5 and adjacent would be 12. So the tangent of angle A is 5 over 12. And then secant, I just remember that's the reciprocal of cosine. And we know cosine is adjacent over hypotenuse. So this must be hypotenuse over adjacent. And we're looking with respect to angle B. So the hypotenuse is 13. The adjacent is 5. So this would be 13 over 5. Okay, so there is the first page done. All right, number 6 is a little bit of a trickier problem. This one we're going to have to do in 2 steps here. So the first thing we're going to do is find the area of this entire sector. So you might remember from earlier in chapter 6, we got this formula, which is the area of a sector. And you can calculate that by doing 1/2 r squared theta. All right, so they do tell us that the radius of this is 10 meters. And we know the degree measure is 72 degrees right here. But remember, to find theta, it has to be in radians if you're using this formula. So what we're going to do is take that 72 degrees and multiply it by pi over 180. And if you simplify that down correctly, it turns out both 72 and 180 can be divided by 36, which is going to bring this to 2 pi over 5. All right, so let's plug that in, and we'll also plug in 10 for our radius. So we end up with this formula. And from here, you could simplify this down. I'm actually just going to plug in to the calculator 0.5 times 10 squared times 2 pi divided by 5 and get it as a decimal, which is about 62.8 square meters. All right, so that's going to give us this entire area. Now we're going to use the area of a triangle formula. This keeps jumping around on me. So to find the area of a triangle, we can use the formula 1/2 AB sine of theta. All right, so A and B are the two sides here. So notice that those are both 10. So A and B are both going to be 10. And then theta is just that angle. Now for theta, when you're using this formula, you can use degrees or radians. It does not matter. Just be aware that if you use degrees, you need to make sure your calculator is in degree mode, which my calculator is. So I'm going to leave it at 72 degrees when I plug this in. And if you plug it in correctly, you should get 47.6 square meters. But remember, that gives us the area of this triangle right here. So to find the area of the shaded region, it's our last step here. What we're going to do is take the area of the entire sector, which was that 62.8, and then we're going to subtract the area of the triangle, which was 47.6, and that will give us our answer of 15.2 square meters. All right. So just kind of two problems in one there. First, you had to find the area of the sector, then the area of the triangle, and then subtract those to get your answer. All right, now they want us to find the perimeter of that shaded region. So that is going to involve a couple of things. So first, what I would do is find, let's see, we'll do this in, pick a new color here. We'll do some purple. So I'm going to find this length first right here. So what I'm doing is I'm looking at this triangle. I'm going to call this 10, this 10, and then this is that 72-degree angle right there. And then we can call this L. Doesn't really matter what you call that. But we can use a few different things. You could use the law of cosines. You could use the law of sines. It really doesn't matter how you find this, but I noticed that this is an isosceles triangle. So if this side is 10 and this side is 10, we can take 180 minus that 72-degree angle, and that's going to leave us with 108 degrees. And these both have to be the same, so these are both going to have to be 54 degrees. All right, I just think using the law of sines is a little bit quicker. So what I'm going to set up is sine of 54 degrees over 10 is equal to the sine of 72 degrees over L. And then we can solve this for L. So we're going to go ahead and cross multiply. We get L sine 54 is equal to 10 sine of 72. And then dividing by the sine of 54 degrees will give us the length of L. So it turns out that L is about 11.8 meters. Okay, so that's this. We have this length right here between the sector and the triangle. And then for the perimeter of the shaded region, we also need to find S. Remember, that's the arc length. So S, we used that formula earlier, remember, is the radius times theta. Whoops, and theta, my hand keeps bumping these pages over here. Theta, remember, has to be in radians, which we already calculated was 2 pi over 5. All right, so go ahead and plug that in your calculator, and you'll get about 12.6 meters. And we want the perimeter, so to find the perimeter, the last thing we're going to have to do is just add the 11.8 meters with the 12.6 meters, and we will get 24.4. All right. Okay, so we're going to switch gears a little bit here, and in number 8, they want us to find the values of the 5 remaining trig functions, given that tan of theta is 40 over 9, and theta is in quadrant 3. And they do recommend making a drawing, so I'm going to start with that. So here is the coordinate plane, and then somewhere in quadrant 3, I always just draw an angle and call that theta, and then drop down the vertical to the closest x-axis. And make sure your theta is always going to touch the x-axis. I've been seeing some really creative drawings when you guys make your triangles, so this is the best way to do it. All right, so now we know tangent, remember, is 40 over 9, which tells us our opposite and adjacent. So opposite that angle would be 40, and it's going to have to be negative if we're in quadrant 3, and adjacent is going to be negative 9. And I know those are both negative because both x and y are negative in quadrant 3. All right, so now we can use the Pythagorean theorem to find the hypotenuse. So I'm going to say negative 40 squared plus negative 9 squared is equal to c squared. All right, so if you plug that in a calculator, you end up with 1,681 is equal to c squared. And then if we take the square root, we get 41 is c. So it turns out that that's a Pythagorean triple. Now, another thing to note is the hypotenuse is always positive. Don't ever make it negative, otherwise you're going to get the wrong signs on your trig functions. All right, well, now that we have this, we can go ahead and fill in for the trig functions. So just really quick here, adjacent over hypotenuse is going to give us cosine. The adjacent is negative 9. The hypotenuse is 41. Sine is your opposite over your hypotenuse. So opposite was negative 40. The hypotenuse was 41. Cosecant is just the reciprocal of sine. So this is going to be hypotenuse over adjacent. So it just flips that previous fraction. Secant is the reciprocal of cosine. So that's going to be hypotenuse over adjacent, or negative 41/9. And then cotangent is a reciprocal of tangent, so that is adjacent over opposite, or 9/40 from what was given here. All right. Number 9. Use your knowledge of 30, 60, 90 right triangles to find the missing side lengths in the diagram below. This problem should be solved without doing any calculations. So what we're going to start with is the triangle that we know more information about, which I believe we're going to have to start with probably the big triangle. So the entire triangle here, if this angle is 30 and this is 90, that means this over here has to be 60 degrees. So what I'm doing is I'm actually looking at this entire triangle without cutting it into two quite yet. And if you remember, if we know the hypotenuse is always double the shorter leg, so if I double 2, I would get this 4 here. So that's what I'm starting with, is that I know that that's 2. And then the longer leg is always the shorter leg times root 3. So this is going to be 2 times the square root of 3 to give us x. All right, so we got x. All right, and now I'm going to do the second part in blue here. So with that one, now we're going to look at, I'm actually going to look at the smaller triangle. But you can do this with the medium-sized one, but I think it's going to be easier to do it this way. So remember, your hypotenuse is always double the shorter leg. So now in this blue triangle here, I know this is going to have to be 1 from here to here. Because if I double 1, I'll get the hypotenuse. And then for root y, you can take the short leg, which is 1, times the square root of 3, and that's going to give you y right here. So 1 times the square root of 3 is just root 3. Okay, I could have, now this last part is just kind of an extra, you don't really need to do this, but I could have used this medium triangle where I knew that the hypotenuse was 2 root 3. And then like the 2 would be actually my short, sorry, where was I going with that? Actually, I don't know that that would be any easier, so I'm not going to even go into that. Since my hypotenuse is 2 root 3, I mean, you could divide that by 2 to get this 1 root 3, but I think using the smaller triangle is easier. So I don't want to confuse you guys. Just ignore that last thing I did in green. All right, page 3. So we're getting into some word problems now. And in 10 and 11, it says to answer each question using a trig ratio of a right triangle. So we're not going to get into the law of sines or the law of cosines quite yet. So this is still using SOHCAHTOA, and it wants us to also make drawings. So get your art skills handy. In 10, it says a 100-foot line is used to tether a helium balloon to the ground. All right, so we've got this balloon here. Look at that beautiful balloon. Woo. Okay, and then it's kind of blowing. It's not going straight up and down. So this is the 100-foot tether, or the 100-foot string, or whatever you want to call it. And then because the wind is blowing, what's happening is it's making a 75-degree angle with the ground. So here's the ground, and then this is 75 degrees. And then we want to know how high the balloon is above the ground. So we're going to drop that vertical, and then we can call this right here the x. Alrighty, so you can see we have the opposite of the angle. The 100 is actually the hypotenuse. So if you're thinking SOHCAHTOA, this is going to say the sine of the given angle is equal to your opposite over your hypotenuse. All right, so we can go ahead and solve that by multiplying both sides by 100. If you plug that in a calculator, please make sure you're in degree mode, and you should get 96.6 feet for that height. All right. Okay, number 11 is another SOHCAHTOA problem, but this one's a little more complicated. It says, from the top of the U.S. Bank building in downtown La Crosse, the angle of depression to a point on the Wisconsin side of the Mississippi River is 22.6 degrees. Okay, let's just start with that. So here is the U.S. Bank building. And so here is the horizontal, like if you were staring straight out from that point. And then an angle of depression, okay, we'll say this is the Wisconsin side of the lake right here. So this is the grass. And then here's the river. And I think we're eventually going to get to the Minnesota side, or Pettibone Park. So here's what's going on. You're looking down. So this is an angle of depression right here of 22.6 degrees. All right. Then you look to the other side of the river at Pettibone Park, and that angle of depression is 5.5 degrees. All right, and we're going to use this information to try to find I think we want to find the width of the river. Let me see. Find the distance across the river between the 2 points. So we are trying to find that distance right there. So we're probably, since we're only allowed to use SOHCAHTOA, we're going to be looking at a couple of right triangles here. The first right triangle that I'm going to work with is this one here. All right, so let's see if we can find out some information with this. What I would do first, and there's more than one way to do this, is I notice I've got some parallel lines here and transversals. So using that idea, if this right here is 22.6 degrees, this right here is also going to be 22.6 degrees. You could do some stuff with like subtracting from 90, but I think this is probably the quickest route. All right, so we got this right angle here, and we know the top of the bank building is 130 feet above the ground, or above the level of the river, actually. And now we're going to call this, let's say this is just length A. All right, so we've got that's adjacent to the 22.6, and then 130 is opposite. So that is actually, if we have opposite and adjacent, we're going to be using tangent. 22.6 degrees is our opposite, which is 130, over our adjacent, which I just called A. So, whoopsies, sorry about that. So first we're going to take and multiply both sides by A to get it out of the denominator. And we're going to get A times the tangent of 22.6 degrees is 130. And then we can go ahead and divide by 22.6 degrees. So hopefully you have your calculator handy. So these are going to cancel, and A, when you plug 130 divided by tan of 22.6 degrees in your calculator, we get 312.3 feet. All right. So the next thing we're going to do now is find the length here using this larger right triangle, which I'm outlining in purple here. And the same idea as before, this angle here is going to match the 5.5 here. And again, you could do some stuff with 90s and you could find this angle up the top, but I just like to use the parallel lines and the transversals to find the matching angles. So that would be 5.5 degrees right there. So again, this 130 is still opposite. Now we'll call this length here, the entire length, D, sure. And then we'll find that using another tangent ratio. So we'll say that our opposite, or tangent of the angle, is equal to our opposite over our adjacent. And if you solve that for D, same way we did before, we're going to start by multiplying by D. I'm probably going to run out of room here, but you get D tan of 5.5 is equal to 130. And then you can go ahead and divide by tangent of 5.5 degrees. And if you do that, you're going to end up with D is 1,350.1 feet. So now to find that length of X, which is the length or the width of the river, we're going to take the entire distance that we just found, the 130, I keep saying 130, 1,350.1 feet. And then we're going to subtract 312.3 feet. And if you do that, the width of the river ends up being 1,037.8 feet. All right. So that is the width of the Mississippi according to this problem. Not sure what it is in real life. You could Google it and find out if you are curious. Okay, so now let's see what we've got next here. Number 12, still, I think, going to be using some right triangle trig here. Actually, for number 12, this is going to be the area of a sector, so let's kind of take a look here. It says that you have a radar system set up to track approaching storms. The radar is set to reach 200 miles. And cover an arc of 150 degrees. Find the area of the sector that the radar covers. Okay, so I'm just going to draw in a coordinate plane here to kind of visualize this. And then we know that it's set to reach 200 miles. So say that this is like where the radar is. You can go 200 miles out. So the 200 is actually your radius. And then it scans an arc of 150 degrees. So this is also 200. And then this angle in here is our theta, which is 150 degrees. And then it can scan everything in this region here. Okay, So we want to know how much area it can cover. And you can probably see that this is going to be using the area of a sector formula, which is 1/2 r squared theta. As always, theta we have to change into radians. So we're going to multiply by pi over 180. And if you simplify that down, I see that 15 over 18 could still be divided by 3. And you will get 5 pi 6 for theta. So now we can go ahead and plug in our radius and theta. All right, so at this point you could simplify it. To be honest with you, I just usually plug it in a calculator right away. And you're going to end up with 52,359.9 square miles for that one. All right. Okay. Number 13 wants us to solve the triangle. So now we're going to be getting into the law of sines and law of cosines. With this one, notice that we have a angle, side, angle. So this is angle, this is the included side, and then this is another angle. So this is going to be a law of sines problem. And when you solve a triangle, you want to find out everything you can. So I write down the things I don't know. So I don't know angle C. I don't know little b. And I don't know little a. So I know those are the 3 things I need to find. So first, let's find angle C. That's actually going to be the easiest because I can just take 180 degrees minus the 2 given angles. So angle C I can get right away is 78 degrees. So there is the first thing I know. All right, now you can find either little b or little a. It does not matter which one you do first. I'm going to do little b just because I put it next in the line. So what I can start with is, remember, now we know that this is 78 degrees. So we have a pair. So we can say, oops, I don't know why I put an M. Sine of 78 degrees, which is across from the 16, is equal to sine of 65 degrees over little b. All right, so if you cross multiply this, we get b sine of 78 degrees equals 16 sine of 65 degrees. And then we can go ahead and divide by 78 degrees. And we're going to get b equals, plug that in a calculator, and you'll get 14.8. All right, and then little a, same thing. We're going to start with still, we know that sine of 78 degrees over 16 is going to equal, and now to find little a, we're going to use the 37 degrees that's across from it. Okay, and then same way to solve this. A sine of 78 degrees is equal to 16 sine of 37 degrees. And then if you divide by sine of 78 degrees, you'll get a by itself, which is 9.8. All right, so we know all 3 angles and all 3 sides, so that is solved. Okay, moving right along here, we're on the last page, so some more word problems for you. In 14, it says a surveyor measures the 3 sides of a triangular field to be 114, 165, and 257 meters. What is the measure of the largest angle of the triangle? All right, so we've got this triangle here, and it really doesn't matter what shape you make it, but I know that 2 of the sides are 114 and 165, and then the biggest side is 257 meters. And we talked about this a little bit earlier in one of the word problems from the homework. The largest angle is always across from the longest side. So this is the angle that we're trying to find. And it really doesn't matter what you call it. I'm going to say that this is A, this is B, and this is C. So we're going to use the law of cosines to find angle A, since it wants us to find the biggest angle. So we can say that the cosine of A, which we don't know, and now here's where you have to be careful when you're using this formula. When you're finding an angle using the law of cosines, this side across from it always comes first. So in other words, little a is going to be first. So this is going to be 257 squared, and then it's minus the other two side lengths squared. So in this case, minus 165 squared minus 114 squared. And you can flip-flop the order of the 165 and the 114. That does not matter. But the 257 has to go first. And then that's over negative 2 times, again, the other two sides, so the 165 and the 114. And again, those can be flip-flopped, so the 114 could go before the 165. Now, when you plug this in your calculator, you are going to need to make sure you put parentheses around the numerator. I would also put parentheses around the denominator just to be safe, but you don't really need them. Okay, so I, just to be on the safe side, put them both in parentheses when you divide. All right, so now we've got that, and we can plug that in our calculator, and you're going to get cosine of A is equal to some decimal, and I would at least do 4 decimal places. So I'm going to say negative 0.6845 is what you should get when you plug that in. Now remember, we want angle A, so we're going to have to take the inverse cosine to get cosine out of there. So in your calculator, again, make sure you're in degree mode. Plug in cosine inverse of that decimal, and you can use that second answer button if you want to get a more exact answer. But if you plug it in as shown, you should get about 133.4 degrees. And that seems like a reasonable answer because this is a large angle. I'd expect it to be, you know, kind of large, which it is. All right, so now to find the area of the triangle, you can do one of two things. You can either use Heron's formula and plug in the side lengths as like your A, B, C, or you can use the formula that we used previously, the 1/2 AB sine theta. Doesn't matter, but since we already took the time to find this angle, I think it'll actually be easier to use this formula, 1/2 AB sine theta. Could you say that this is little a, this is little c, and this is little b, and then find the semi-perimeter and then use Heron's formula? Sure. You're going to get the same answer either way. So in this case, to find the area, we're going to do A equals 1/2, and then you use the two sides that surround the angle that you're using. So 165 and 114 in this case. So when we're using this formula, a couple things are actually changing here. When you use this in a specific problem, it's not always technically A and B. In this case, it's actually C and B because those are the two sides that surround angle A, which is the angle that we're using. All right, so that's why I'm not actually using little a and little b. So sometimes you gotta manipulate the formula a little bit to get it to how you want. All right, so now we've got our formula plugged in correctly using the 165 and the 114, and then the included angle, which is that 133.4 degrees. If you plug that in your calculator, you are gonna get 6,833.4 square meters. And again, you could use Heron's formula. If you do, you should still get very close to that same answer. So if you want to try it out that way, that's okay. Just make sure you get something close to 6,833. Okay, number 15, a utility tower located on the side of the bluffs casts a shadow 67 feet down the hill. The angle of elevation of the sun from the point at the bottom of the shadow is 47 degrees, and the side of the bluff makes a 19-degree angle with the horizontal. And we're going to use that information to find how tall is the utility tower. Okay, so let's start with our drawing here. So here is a bluff. And we know that that angle to the horizontal right here is 19 degrees. And then what we've got going on is there's this tower on the bluff. So here's the tower. And somewhere over here, the sun is shining. Sun, 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 sun. And that is shining at this angle here. Whoops. To the ground. Whoops, I'm gonna just make my tower taller to make that work. Ta-da! Okay, and that angle that the sun is shining is 47 degrees. Oops, I was gonna do that in a different color and I thought I clicked it. All right, so this here is 47 degrees. And then we are trying to find the height of the tower. So I'm going to call this right here X. Okay, so we can assume that this right here is going to drop straight down and be a right angle. So we're going to have to do this in a couple of steps. The first step is going to be just to find as many missing angles as we can. So first in this right triangle down here, we can find that angle by doing 180 minus the 90-degree angle minus the 19 degrees. So that angle is going to end up being 71 degrees. And then that actually makes a 180 with this angle. So this is going to have to be 109 degrees. And then you can take, to find this angle, we know they're both going to have to add up to 47. So for that to happen, this is going to have to be 28 degrees. And now, one more time, we can do 180 minus the 109 minus the 28. And that's going to give us 43 degrees for this angle up here. Okay, so what we're going to do is actually focus on this triangle. Running out of colors. I'm going to pick a new color here. Give me a sec. We're going to use this triangle right here. All right. So, I'm not sure. Just give me a sec. Whoops, thought I could do something, but I don't want to just fudge up this, so never mind. Okay, forget it. We're going to take and use that triangle with the 109 degrees to find our X. So I'm actually just going to try redrawing it because there's just too much going on in this picture. So I'm taking, just now that I have all these angles filled in, I'm looking at that top triangle. So the one with the 28 degrees. And then down here was the 109. And then up here was the 43 degree. Okay, and then my X is here. So I also know one other thing. I know that the bluff, or this tower is 67 feet, or its shadow is 67 feet long. So this here is 67. So this was the shadow right here that the tower was casting down the bluff. So that's the 67 feet. All right, so now we have enough information to set up a law of sines, because I know this 43 degree angle across from the 67, and I know the 28 degree angle across from the X that I'm trying to find. So I'm going to say the sine of 43 degrees over 67 is equal to the sine of 28 degrees over x, and now I can cross multiply. So x sine 43 degrees equals 67 sine of 28 degrees. And then we can divide by the sine of 43. And if you plug that in your calculator, you will get x is 46.1 feet. And that seems like a reasonable answer because the shadow should be a little bit longer in this situation. Okay, our second to last problem says that a plane flies 810 miles from A to B with a bearing of 75 degrees north of east. Okay, so let's start with that. So we've got a plane here, and north of east means if you go north and then 75 degrees east would be this angle here. So that is north 75 degrees east. And it says that you're flying that direction for 810 miles. All right. Then what happens is you fly from B to C. So we're going to assume that this is point A and then this is point B. So then you go from B to point C with a bearing of 32 degrees north of east. All right, so I think I'm going to have to move this stuff down a little bit. So let me move this, otherwise I'm going to run out of room. Okay, so now you go again north of east means you would have gone north, but then you turn and go east. And now this angle here is 32 degrees. It's a little hard to see, but that is 32 degrees right there. And then you get to point C here. All right, and then that was a distance of 648 miles. And we want to know how far is it from your starting point. So we're trying to figure out this. Okay, so here's what you can do. We're going to use a little bit of, what am I trying to say? Some parallel lines with transversals here. And I'm noticing that my laptop is going to die and I do not want to start this video over. So you're going to have to just bear with me for a sec. I'm going to go get my charger. All right, thanks for being patient. I just did not want to start that video over and my computer was at about 6%. So we are in the middle of problem 16 here, so hopefully you got a chance to draw that drawing. And what were we doing? Oh yeah, we were going to say parallel lines with transversals to get some missing angles here. So I'm going to get this highlighter here and kind of use that to illustrate what's going on. So these dashed lines are the two parallel lines that we're going to be looking at. And then you can think of this line right here as a transversal. So think back to geometry. And we've got some alternate interior angles. So if this is 75 right here, it turns out that here is also a 75-degree angle. And now we know that this right here with that dashed vertical line makes 180 degrees. So that's going to have to be 105 degrees there. And now we have that entire obtuse angle at B is 137 degrees. Okay, so maybe it will help to redraw this so you can see what's going on here. So this is the 137 degrees that we just figured out. This is 810, and this is 648. So I'm going to call this here little b, since it's across from this angle B. And we can use the law of cosines to find b. All right, so we're going to say b squared is equal to, and then you do the two sides that surround the angle that you're using. So in this case, 810 squared plus 648 squared minus 2 times 810 times 648. And then it's times the cosine of the angle across from little b, which is 137 degrees. All right, so here's what we need to do is just plug that all in your calculator in one big line. That is always how I do that. So then we get b squared, oops, sorry about that again. We're going to get b squared is equal to a really big number, so I'm just going to jot down that number for reference. So looks like 1,843,749.86. And then remember, we need to take the square root of that to get b by itself. So that's where I would do second square root, second answer. And you're going to end up with about 1,357.8 miles. All right. And that seems like a reasonable answer based on our other two lengths. Whew. All right, we're almost there. So now we have triangle ABC with angle A measuring 58 degrees. Actually, I'm going to call the top one A and then this B and C. Okay, so this is 58 degrees here. And then little a is 45 and little b is 50. So notice this is an angle side triangle, or an SSA. So we know that this is the ambiguous case in which we might have two triangles possible. So first, let's just solve it like we normally would. Notice that the first angle we can find is angle B here, since we know little b. All right, so let's say sine of 58 degrees over 45 is going to equal sine of b over 50. If we cross multiply, we get 45 sine b is equal to 50 sine of 58 degrees. And then we can divide by 45, divide by 45. We end up with sine of b is, that decimal is about 0.9423. And then we're going to take the inverse sine to get b by itself. And that ends up being about 70.4 degrees. Okay, so that is our first angle B. And now we can use that to find angle C. So we know angle C is just going to be 180 minus the given 58 degrees minus the 70.4 degrees, and you're going to get 51.6 degrees for angle C. All right, and then we can do one last law of sines here to find little c, and I'm just going to try to smush this in down here. So sine of 51.6 degrees over little c equals sine of 58 degrees over 45. And I'll leave that for you to solve. Just take my word for it, or, hopefully you can find some more space. But if you do that correctly for this, you're going to get C is 41.6. All right, so that is for triangle 1. So that is, we'll say triangle 1, that's my work for that. Okay, so triangle 2 now is you always go back to the first angle that you found, which remember was angle B here. So now we're going to see, could my angle be an obtuse angle? Could it be the supplement of that? So for triangle 2, this is going to be 109.6 degrees. So we're going to see if that will work. So if I say that angle B is now 109.6, well, if we do 180 minus the given 58 degrees, and then minus this new option for angle B, well, that still leaves us with 12.4 degrees. So we'll say C prime is 12.4 degrees. So we did have enough left over to have a very, very small angle C. Okay, so this is actually our angle B prime, and we can see that there was enough leftovers with that new angle B and angle A being 58 degrees to have an other option for angle C. So the last thing we need to do then is find the new side C, which is going to be using sine of 12.4 degrees over little c is sine of 58 degrees over 45. And if we cross multiply and solve that correctly for little c, you should get about 11.4. All right. So this would be all of our information for triangle 2. So there were actually 2 possible triangles here. All right, so that is the review. I hope that helps and you were able to get what you needed from that. Have a great rest of your day.